We will start today with one of the topic which is called as coordination compound and of course the organometallic compounds. Of course, as per the CBSE syllabus, we are supposed to take up few definitions, right? So let's first take up what are the learning objective of this chapter. So after studying this chapter, you should be able to give the postulates of Werner theory, number one. Number two, you should understand few definitions which are actually being able to define the coordination compounds, include the central atom, the ion, the ligand, the coordination number, oxidation number, of course, what is coordination entity, what is coordination sphere, what kind of complexes are homolipidic and heterolipidic complexes. Then we should also learn the nomenclature of the organic compounds. Then, of course, the reverse from the nomenclature to writing the structure. Then the most important is to know the nature of bonding, the magnetic behavior in, of course, the coordination compounds using valence bond theory and the crystal field theory, which is called as CFT. Let's start first. There is a term which is exactly called as double salt. So when I'm talking about a double salt, as the name suggests, a double salt is nothing but it is basically a, a substance or a salt which is made up of by the combination of two different salts. Let's start with an example. Suppose if I'm talking about potash alum. Potash alum has a formula of K2SO4 dot Al2SO4 whole thrice dot 24 water of crystallization or 24 water molecules. I can also call it as potassium aluminium sulfate. So as we can see that the two salts, potassium sulfate and aluminium sulfate, are nothing but they are in equimolar mixture, or they are actually being formed by the combination of two salts with, of course, water of crystallization. Another example is ferrous ammonium sulfate or ferrous sulfate ammonium sulfate with, of course, 6 water of crystallization, which is of course called as Mohr salt. So what is a double salt? A double salt is basically a molecular compound which exists only in the solid state and which has the tendency to lose its identity whenever it is dissolved in water. What I mean to say, that it lose its identity in the aqueous solution. That means if I am trying to dissolve, suppose potassium sulfate, it will try to give you the test of potassium, it will give you the test of sulfate, it will give you the test of aluminium, and so on. That means it will give you all the free ions which are being present over here. In the same way, if I am talking about Mohr salt, it will try to give you the test of ferrous ions, the ammonium ions, and of course the sulfate ions also. That means that it is going to lose its identity in the aqueous solution. So that's why we used to call them as kind of unstable salts, or double salts are basically which can lose their identity in the aqueous solution. The things will become more clear if I'll try to talk about coordination compound. See, when I'm talking about a coordination compound is basically that which consists of a central atom, right? A central atom, of course, is nothing but it will be a d block element, of course, which has vacant d orbital, as we have done it in d block elements also, that the d block elements or the transition element have the tendency to accept the lone pair of electrons from the ligands, which are of course acting as the Lewis bases capable of donating the lone pair of electron to this central atom. So if I am talking about what is basically a coordination compound, is a coordination compound is basically that which consists of a central atom or a central ion surrounded by a fixed number of ligands which are capable of donating the lone pair of electron to this central atom, and they are capable of forming sigma bonds. These ligands are nothing but they are basically called as Lewis bases, as we have already done. Lewis bases are lone pair donators. They are lone pair donor. So let's go to the definition of coordination compound. A coordination compound is basically that in which a metal atom or an ion is coordinated to two or more anions or neutral molecules by, of course, coordinate or dative bond, retaining, the most important point here is it is capable of retaining its identity in the solid as well as in the aqueous solution. For example, if I'll try to take up CuNH3 whole fourth sulfate ion, and of course, one of the example of a coordination compound, once it is being dissolved in water, it will give you CuNH3 whole 4 2 positive. That means if I'll try to ionize it in the aqueous solution, if you can see, if I'll try to ionize, it will give you CuNH3 whole 4 2 positive plus sulfate ions. That means it is not going to lose its identity in the aqueous solution. This will retain its identity in the aqueous solution. Only this sulfate ion, which is outside the coordination entity, which is of course this bracket, which is also called as a counter ion that we will study later on, is capable of giving the test for this. We will be taking up the different kind of coordination compound, right? Let's start one by one. I can give you first example of coordination compound. Suppose CuNH3 whole 4 2 positive. So this ammonia is acting as a ligand over here. Another example is NiCO4. Here carbonyl is acting as a ligand over here. This is the central atom, and this bracket is basically called as the coordination entity or sphere. Another example is FeCO5. FeCO5 means if I have this is also central atom iron, carbonyl group CO with 5 ligands, of course ligands are CO only. Now coordination compounds are basically divided into the following type. When I am talking about coordination compound, they are basically, as I said, are divided into three types. Number one, cationic. Number two, anionic. Number third, neutral complexes. The best example, let's start. CuNH3 whole 4 2 positive. Since it is bearing a positive charge, that means it is a cationic complex. AgNH3 whole 2 is positive, again a cationic complex. NiNH3 whole 6 2 positive is also a cationic complex. Similarly, if any complex is getting a negative charge, AgCN whole 2 is negative, FeCN6 3 minus, FeCN6 4 minus, CuCl4 2 minus, they all are nothing but they are anionic complexes. Now let's take up NiH2O whole 4 Cl2, no charge. CuNH3 whole 6 Cl3, no charge. NiCO4, no charge. FeCO5, no charge as such. These all are nothing but they are neutral complexes. Now let me first take up how to actually split up the coordination compound, right? Suppose I have this compound K4FeCN6. If I'll try to ionize this, since potassium is K positive, and how many number we have? We have 4. So I can write here 4K positive plus, in order to maintain the charge, 4 positive means it should be FeCN6 4 minus. Now in the same way, K3FeCN6 can be ionized to give you thrice of K positive plus FeCN6 3 minus, because 3 positive and 3 minus, that means it becomes neutral now. So this is how we used to split up them. Another example is CONH3 whole 6 Cl3. So it becomes CONH3 whole 6 3 positive plus thrice of Cl minus ions. That means chloride here can ionize itself, because it has a 1 minus charge. So Cl minus 3 chloride ions, CONH3 whole 6 3 positive. So 3 chloride ions. Now in the same way, CrH2O whole 4 Cl2 NO3. So this is minus 1. So it becomes plus 1. So if I'll try to ionize, it becomes CrH2O whole 4 Cl2 positive plus NO3 minus. So this is how the coordination compounds are actually being ionized. As I was telling you, this bracket is nothing but it is called coordination entity, right? So if I'll ask you what is basically a coordination entity is, a coordination entity is basically that which consists of a central atom or an ion which is bounded to a fixed number of ligands. Here, of course, we have cyanide. These ligands are basically Lewis bases, as I said. So I gave you the example of this also. COCl3 NS3 whole thrice is one of the coordination entity in which cobalt is the central atom, which is surrounded by 3 ammonia ligands and 3 chloride ligands. So that's coordination entity. Now, the most important thing right now is, why did I take up the ionization of this? I've taken up the ionization just to take up the difference between the coordination compound and the double salt. See, as I said in the beginning itself, a double salt is basically obtained by the combination of two different salts, which crystallizes together, of course, as a single substance or a single salt. But when you try to dissolve them, you'll find that it is going to lose its identity in the aqueous solution. I thought I told you very clearly that it means if I am going to ionize this double salt inside the water, it is going to give you the test of potassium, sulfate, aluminium, all the ions. It's free. They all are free. But it never happened in the case of coordination compound. Only the ions. Of course, I said they are base specified, or specifically I said they are called counter ions. Only the counter ions which are kept outside the coordination entity will try to give the test. Rest all are not capable of. So as I said, the double salts, they lose their identity in the aqueous solution whenever they are dissolved in water. As I have given you FeSO4, that's more salt, will try to give the test of ferrous ions, water, ammonium, sulfate, etc., etc. And in the same way, potassium sulfate also will give you the test of potassium sulfate, aluminium, etc., etc. But a coordination compound is a molecular compound that is result from the combination of two or more simple molecular compound, and it is going to retain its identity in the solid as well as in the dissolved state. That is the most important point that we have discussed so far, is the difference in between a coordination compound and a double salt is. I have also taken up the ionization, as I was talking about. CuNS3 whole fourth SO4 can be ionized to give you CuNS3 whole 4 2 positive, and of course I can say 2 minus, then of course this should be 2 positive. In the same way, 4 of K positive plus FeCN6 4 minus. So this is 4K positive plus FeCN6 4 minus. Now we will be taking a few definitions related to the coordination compound. The first one is nothing but it is, of course, it is not the first one, it is the fifth one, called central atom or ion, and of course the counter ion. I've already taken up the central ion is nothing but they are basically the d block elements which contain the d orbitals or vacant d orbital, which are capable of accepting the lone pair of electrons from the ligands. That's why I can call them as Lewis acids. So in a coordination entity, the atom or ion to which a fixed number of ions or groups are bound in a definite geometrical arrangement around it. These central atom or ions act as Lewis acids, usually d block elements, as I said. For example, NiH2O whole 4 Cl2. This nickel is acting as a central atom, cobalt is acting as a central atom, or Rn is acting as a central atom over here. And all the ions that are actually being present outside the coordination entity are nothing but they are basically called as what counter ions are. Another term that we are going to take up right now are ligands. As I've already told you, ligands are nothing but they are the Lewis bases which are capable of donating the lone pair of electron to the central atom, and of course through the dative bond or coordinate covalent bond. This we have already done. When I started the chapter, I told you very clearly that ammonia is acting as a ligand over here, right? Now let's go to the classification of the ligands. When I'm talking about the classification of ligands, they are basically being classified in three ways: on the basis of charge, on the basis of the number of donor sites which are being present, and of course on the basis of the bonding. Let's start one by one. I'm going to take up these two simultaneously. That this is negatively charged Cn minus F minus cyanido, fluorido, chlorido, nitrito, N, nitrate, then hydroxo, oxo. This has a positive charge, nitronium, because positive charge always ends with em, nitrosonium, and so on. Neutral ligand like water, ammonia, etc., NH2OH have lone pair of electrons which are capable of donating them. But the most important classification that we are going to take up is on the basis of number of donor sites that are present in it. And the most important term over here is monodentate. Monodentate means which contain only one donor site, as in like water has only one donor site or one donor atom. and that's nothing but it is oxygen over here. Ammonia has again one donor atom, that is nitrogen. That's why it's called monodentate ligand. Monodentate means which has only one donor site or one donor atom. So monodentate or unidentate ligands, ligands with one donor atom, it can be neutral or anionic with, of course, the specific name. Bidentate ligands are basically which contain two donor sites. One of the best example is oxalate ion. So we always write oxalate ion in this way, COO, COO, and of course we can write oxalate as OX in abbreviation, or some other books they write C2O4 2 minus. There is another ligand which is one of the most important example of a bidentate ligand, and that's called ethane 1 comma 2 diamine, also called as ethylene diamine, where of course there are two donor atoms, right? Just like oxalate ion has this as the donor atom and this also as the donor atom, means there are two oxygen atom which are donor atom. Here there are two nitrogen atom which are donor over here. One is this, one is this. That's why ethylene diamine or ethane 1 comma 2 diamine, one and only the same thing, is nothing but it is a bidentate ligand. In the same way, any ligand which contain three donor atoms are called tridentate, which contain four donor atoms are called tetradentate, which contain five donor atoms are called pentadentate, and of course one of the best example which I'm going to take up right now of hexadentate with six coordinating atoms is EDTA, which is actually called as ethylene diamine tetraacetic acid, that we will be discussing right now. Let's start. Neutral or monodentate water is called aqua, ammonia is called amine, carbonyl, NO, nitrosyl, C5H5, C5H5N is called pyridine. The donor atom, of course, one donor atom because they are monodentate ligands. In the same way, fluorido, chlorido, bromido, iodido, hydrido, nitrito. Of course, it should be called nitrito N. Then we have sulfide, which is thio, oxo. Then cyano or cyanido has carbon. Acetate is called acetato, right? Then SCN is called thiocyanato. NCS is called isothiocyanato. OH is called hydroxo. ONO is called nitrito or nitrito O. HS minus mercapto, peroxo, and so on. These are few examples of monodentate, neutral and anionic ions. Then, as I said, we have already done about oxalate ions. We have done about sulfate, glycinato, DMG, dimethyl glyoxim. We have done about phenanthrene. Ethane 1 comma 2 diamine again is abbreviated as EN. We have already done this, that here it is called En. Now, the next is a example of few polydentate ligands. This is EDTA, ethylene diamine tetraacetic, which has 1, 2, 3, 4, 5, 6, 6 coordinating atoms. Then there is a term which is called denticity. The number of coordinating groups that are present in the ligand is nothing but it is exactly called as its denticity is. As usual, if I'll say denticity, that is always related to teeth. That means the ligands are being classified on the basis of the coordinating atom or coordinating site that are present in it. So ligands, of course, monodentate, bidentate, tridentate, tetradentate, depending upon the number of coordinating sites or coordinating atom that are present in them, is nothing but it is called as the denticity. If, of course, if I'll say a monodentate, it will have its denticity is 1. Bidentate has a denticity of 2. Tridentate has 3, and so on. Next, I thought I have already discussed about coordination entity with you. That is, a coordination entity basically consists of what? A central atom surrounded by the fixed number of ligands. That's basically called as a Lewis base. Example we have already done. Then we have a coordination sphere. When I'm talking about coordination sphere, it has again the central atom or ion, and the ligands attached to the central atom are enclosed in a square bracket, collectively termed as coordination sphere. The ionizable group, which I was talking about, is always written outside the coordination entity or entity, is always called as a counterion. Counterion can be in front, or if I'll take up the example CO NS3 whole 6 Cl3, here the counterion is after the coordination entity, will not make any difference as such. The next term that I'm going to take up right now is called homolipidic and heterolipidic complexes. When I'm talking about homolipidic complexes, that means same kind of ligands, or complex in which the metal atom is bound to only one kind of donor atom or ligand, then it is called homolipidic. But if it is attached to different ligands, for example here NS3 whole 4 Cl2, then this is called, or these kind of complexes are called heterolipidic complexes. The next term that we are going to take up right now is called chelating ligand and chelation effect. A very important topic. When I'm talking about chelation, the word chelation or chelate is derived from a Greek word that means claw, or sometimes also called as ring-like structure, sometimes also called as cyclic structure, or as I said, claw-like structure. Now, whenever a bidentate, I repeat, whenever a bidentate or a polydentate ligand is attached to the central atom, forming a ring-like structure, then it is nothing but it is exactly called as a chelating complex. For example, if I'll take up Cu and if I'll try to attach ethane 1 comma 2 diamine, this is ethane 1 comma 2 diamine, where this is donating because this is a bidentate ligand, and again another bidentate ligand being attached. Now you can see here it is forming a cyclic kind of structure, a cyclic kind of structure, or of course a ring like structure. Such kind of structures are nothing but they are called chelating complexes. So I have written here, whenever a bidentate or a polydentate ligand is attached by two or more donor atoms to the same central atom or ion, forming a ring like, cyclic or claw like structure, it is called chelating ligand. A chelating ligand, one of the example I have just now given you, this is the same example it is written. You can also write down this example in this way, and that is, as I said, En. So I can write here Cu En whole twice and of course 2 plus. This is how another way of writing this chelating complex. The most important characteristic right now is chelating complexes are always more stable in comparison to the normal complexes. For example, in one of the board question, this was asked, chelating complexes are more stable than normal complexes. For example, here if you can see, COEN whole thrice 3 positive is more stable than CONS3 whole 6 3 positive, as seen because this is capable of, or this is a chelating complex and this is the normal complex that we come across. That's why the first one will be, or this will be more stable in comparison to this. The next is ambidient ligands. We have already done this term while we were doing organic. The only thing is, whenever I'm talking about cyanide, so this is the ambident ligand with isocyanide. So we can call it as cyanido or cyno. We can call it as isocyano or isocyanido. In the same way, nitro and nitrito are also ambident ligand. Similarly, SCN, thiocyanate or thiocyanato. Here, sulfur is the coordinating atom. And if I am talking about isothiocyanate or thiocyanato, nitrogen is the coordinating atom. Next term that we are going to take up is called coordination number. If I'm talking about coordination number, that means how many ligands are surrounding it. For example, if you can see here, coordination number is 2. Here, coordination number is 6, the number of ligands that are surrounding the central atom. Now, in this case, the coordination number is 4. Here, the coordination number 4. But now, En is a bidentate ligand. The coordination number is not 2. Since it is 2 into 2, 4, 2 into 2, because En is a bidentate ligand, it will attach from two ends, and since there are two, it becomes 4. So coordination number will be 4. Similarly, oxalate is also a bidentate ligand. So 3 into 2 means coordination number will be 6, because oxalate, as I said, also has how many donating atoms or donating sites or donating atoms? 2. So 2 into 3, that means 6. So coordination number will be 6. Di-En, again a didentate ligand. So sorry, a tridentate ligand. So 3 into 2 means again coordination number will be 6. Acetyl acetate is also one of the bidentate ligand. So 2 into 2, 4 plus 2, 6. So total 6 is the coordination number. EDT, of course, need not to tell you, is a hexadentate ligand. So comes out to be 6. Next is oxidation number or state. We will be calculating this oxidation number or oxidation state when we will be taking up the nomenclature part. I will now just take up that this is the central atom or ion. As I said, this is coordination sphere or coordination entity that I have already taken up. This is the charge on the complex. This is the coordination number. These are called as the ligands. I've written the same thing here also. These are called as the counter ions, or which are ionizable ions. This is called as the coordination number. This is of course Cl2 is of course the coordination number. These are ligands, and of course these are this is the example of a homoliptic complex, and this is the example of a heteroliptic complex. The total coordination number in this case is 4 plus 2 is 6. Next is coordination polyhedra. When I'm talking about coordination polyhedra, it's basically related to the spatial arrangement of the ligands, because of which we will be able to predict the geometry of the particular coordination compound. We have already done one of the shortcut, that was LTT stop, where I said very clearly L stands for linear, trigonal planar, tetrahedral, square planar, trigonal bipyramidal, octahedral, pentagonal bipyramidal, depending upon how many ligands are surrounding them. So let's take up one by one. If I'll even leave this, we have 4 ligands. If they are surrounding 4 ligands, or as you can see here, 4 ligands are surrounding. So coordination number 4, it can be tetrahedral or it can be square planar. As I said, tetrahedral or square planar. If 6 ligands are surrounding, then it should be called octahedral. 6 ligands means octahedral. If 5 ligands are surrounding, it should be called trigonal bipyramidal, which is also called TBP. So this is how the coordination polyhedra basically means, is nothing but it is the number of ligands which are surrounding, which able to predict the geometry of the molecule. We are now going to take up the most important theory, and that's basically called as the Werner theory. Before I'll take up the Werner theory, let me take up the most important thing, that still there are certain complexes which was given by Werner are still under investigation. As I said, we will start right now with one of the most important theory, which is called Werner theory. Let me start with the example. The first compound that was prepared by Werner was COCl3 dot 6 ammonia molecules. Now the most important thing over here, the coordination number of the compound which was prepared by Werner was of coordination number 6. Now when he reacted this compound, the most important right now is when he reacted this compound with silver nitrate, as you know, he saw that it was actually giving us the 3 moles of AgCl white PPT. That means all the chloride atoms are nothing but they are actually outside the coordination entity, and that's why he said the compound will be CONH3 whole 6 and of course Cl3, because if you try to ionize this, you will be getting CONH3 whole 6, 3 positive plus thrice of Cl minus. That means It is in 1:3 ratio, and it is capable of showing you the conduction for 4 ions. Now the second compound which was prepared by him was COCl3 dot 5 ammonia molecule. I repeat, COCl3 with 5 ammonia molecules, and when he reacted with silver nitrate, he saw that it was giving the test for 2 chloride ions. That means 2 moles of AgCl was formed. So he concluded that out of 3, only 2 are inside the coordination sphere or coordination entity, and that's why he reached to the structure as CONH3 whole fifth, 1 Cl inside and 2 outside. And of course, as I said, this is a homolipidic complex, and he reached to a heterolipidic complex, heterolipidic with this, because if you try to ionize this, now it will be 2 plus plus twice of Cl minus, because now it is in 1:2 ratio and it is actually conducting for only 3 ions. The next point was he prepared another compound, and that compound was CO Cl3 dot 4 ammonia molecules. And when he reacted this compound with, of course, silver nitrate, he saw that only 1 mole of AgCl was obtained, or 1 mole of silver nitrate was reacting to give 1 mole of AgCl. So he concluded that the compound will be CONS3 whole 4 Cl2, and only 1 chloride is outside the coordination entity, which on ionization will give you CONS3 whole 4th Cl2 plus chloride ions. That means it is in 1:1 ratio, and the total number of ions will be 2 ions. Now, on the basis of this, he prepared another compound. That compound was COCl3 dot 3 ammonia molecules, and it was not at all conducting with AgNO3. So he concluded that none of the ion or counter ion is outside the coordination sphere. All are inside, and that side is not conducting and not capable of giving the test. But there was another point. He prepared as such 2 compounds of this kind and gave the concept of isomerism. And that's why Werner theory was highly successful. Let's start to draw first the structure of the first compound, which was actually being shown by or drawn by Werner. And it was this compound, COCl3 with 6 ammonia. If I'll try to draw the structure, cobalt is at the center. 1, 2, 3, 4, 1, 1. That means I have ammonia, 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 another ammonia over here and here. So total 5, and then 1 will be at the bottom here. Those chloride ions which I was talking about, if you might have seen in my first compound, I've written 3 chloride ions. These 3 chloride ions, they were actually being shown with dotted lines because they are ionizable, or of course they are capable of giving you the test. So on the basis of this, he put forward the postulates, and the first postulate of Werner theory was, in a coordination compound there are 2 kind of linkages that are possible. One is called as the primary linkage, and the second is called as the secondary linkage or secondary valency. The primary linkage or primary valencies are normally ionizable. Why they are ionizable? Because they are capable of giving the test. That's why they are always outside the coordination entity, as I was talking about. Since you can easily make out These chloride ions which are present outside the coordination entity or sphere are nothing but they are what? Ionizable. That's why they were called as or primary valencies. While those which are present inside the coordination entity or entity are nothing but they are called secondary valencies. They are non-ionizable, right? So secondary valencies are non-ionizable. They are present inside the coordination entity and are satisfied by neutral molecules or of course the negative ions. As I said, primary valency is always equal to. Now if I'll try to ionize the compound, you can easily make out from here that the charge on the complex is all because of the counter ion which is being present over here, because it will try to neutralize this. The charge on this is nothing but it is the counter ions or primary valency, and the coordination number is nothing but it is actually equal to the secondary valence. And of course the geometry of the molecule, that means tetrahedral, octahedral or square planar, is always being predicted on the basis of secondary valency. So as I said, the secondary valency is equal to the coordination number and it is fixed for a metal. It can be either 6 or 4. Although as I said, the compound or the coordination compound prepared by Werner was only of the coordination number 6. It also gives the definite geometry. That means, as I said, if the coordination number is 6, the geometry of the molecule can be predicted that it will be, of course, what? It will be octahedral, and if it is 4, that it means it will be your uh, tetrahedral or it can be square planar. But remember, you might have seen when I have drawn these chloride ions, I can do it anywhere. I can draw this chloride ion here also, and I can remove this from here, right? The reason, but ammonia, if you see, I have specifically drawn in an octahedral shape. You can see, because they are able to predict the geometry of the molecule. That means coordination number से geometry पता चलती है, and chloride are or primary valencies are non-directional in nature. That's why it is called coordination polyhedra. And these are the molecules. And this is exercise 9.1 question which I was discussing, that it was non-conducting. I'll take up one question before I'll go to the nomenclature. It is PdCl2 ammonia. Now if you try to react it with silver nitrate, of course it is giving test for 2 chloride ions. That means both the chloride ions are outside the coordination sphere. So I can write down the name of this compound or structure, PD NH3 whole 4. The coordination number is 4 and both the chloride ions are outside the coordination entity. That means if I'll try to ionize, I'll be getting PtNH3 whole 4, 2 positive plus twice of chloride ions. So secondary valencies are 4, which is of course the coordination number, while the primary valency are 2. Here again there are 2 chloride ions. So both the chloride ions will be outside the coordination sphere. So the formula will be NiH2O whole 6 and Cl2. And if I'll try to ionize, of course, I'll be getting NiH2O. NiH2O whole 6, 2 positive plus twice of Cl minus. There are 6 secondary valencies and of course 2 primary valencies. In the next example, again, no test, no silver chloride precipitate is obtained. That means all the coordination or all the count, all the ions are nothing but they are inside the coordination sphere. So 4 here and 2 chloride ions. That means 6, total of 6. So I can write down this compound as PtCl6. And what about these 2 hydrogen? I can put these 2 hydrogen over here as H2. So if I'll try to ionize this, it become 2H positive plus PtCl6, of course 2 minus. So here again the coordination number is 6. The next is COCl3 4 ammonia, and Now it has only one chloride outside the coordination sphere. So I will write CONS3 whole fourth, two chloride inside and one chloride outside, because it become minus and plus. So the coordination number 4 plus 2 is 6, and one counter ion outside which is giving the test. Now in this case there is none of the chloride ion which is giving the test, means two ammonia and two chloride are inside the coordination sphere. So I can write down PT NH3 whole twice and Cl2. This is the correct option. So if you can see PT NH3 whole Cl2 and none is present outside, that's why it is not going to give you any ions in the solution, because nothing is there in the outside the coordination sphere or entity. But here the secondary valencies are nothing but it is 2 plus 2, it is 4.